Welcome to this problem walkthrough. Today, we'll be exploring problem number 258, titled Add Digits. In this problem, we aim to repeatedly sum the digits of a number until we arrive at a single-digit result. It's a classic problem involving number manipulation with both straightforward and optimized approaches. Let's dive in. In this problem, we are tasked with repeatedly adding the digits of a given integer until we arrive at a single-digit number, which we then return as the result. Let's look at an example to clarify this. If the input number is 38, we begin by adding its digits. 3 plus 8 gives us 11. Since 11 is not a single-digit number, we repeat the process by adding its digits. 1 plus 1 gives us 2. Now that we've reached a single-digit number, our solution for this input is 2. This process continues similarly for other examples. For instance, if the input number is 0, it's already a single-digit number, so we simply return 0 without any further calculations. Another example is when the input number is 1, 2, 3, 4, 5. Here, we start by summing its digits, 1 plus 2 plus 3 plus 4 plus 5, which results in 15. Since 15 is not a single-digit number, we continue by summing its digits again. Adding the digits of 15 gives us 1 plus 5, which equals 6. Since 6 is a single-digit number, we return this as the output. Now, let's consider some important details about the problem. The input number is guaranteed to be a non-negative integer, ranging from 0 to 2 billion, so it's computationally manageable. Additionally, this process of summing digits is mathematically known as the digit root calculation. There's a useful property of digit roots that allows us to solve the problem in constant time by using the formula, number 1% 9 plus 1, except when the number is 0, in which case the result is simply 0. This mathematical insight can make our solution highly efficient. To begin, one straightforward way to solve the problem is through the brute force approach. The idea here is simple: we repeatedly sum the digits of the number until we're left with a single digit. This involves breaking the number into its individual digits, adding them together, and replacing the original number with this sum. If the new number is still greater than or equal to 10, we repeat the process. This continues until the number is less than 10, at which point we return it as the result. While this approach is easy to implement, its time complexity is d log 10 number, where d represents the number of iterations required to reduce the number to a single digit. Each iteration requires us to process all the digits of the number, which takes log 10 number time. On the positive side, this approach uses constant space, as no additional memory is needed. However, for very large numbers, repeatedly calculating the sum of digits can make this approach relatively slow, which is a trade-off to consider. Now, a more efficient way to approach this problem is by leveraging an optimized mathematical method known as the digital root. This takes advantage of a pattern in modular arithmetic, allowing us to directly compute the result without needing to iterate through the digits. The logic here is based on the fact that repeatedly summing the digits of a number is equivalent to reducing it modulo 9. For example, the number 38 sums to 3 plus 8 is equal to 11, then 1 plus 1 is equal to 2, which matches 38%. 9 is equal to 2. Using this insight, we can derive the result using a simple formula: if the number is 0, we return 0. Otherwise, if the number is divisible by 9, we return 9. For all other cases, the result is simply number %9. This approach is highly efficient, as it involves only a constant number of calculations, giving it a time complexity of 1. Additionally, it uses 1 space, making it an excellent choice for handling large inputs efficiently. This mathematical method has clear advantages, but there are trade-offs to consider. It is highly efficient, eliminating the need for iterative computations and making it well-suited for very large numbers. However, it requires a deeper understanding of modular arithmetic and the digital root concept, which might make it slightly harder to grasp at first. Another option to solve the problem is through recursion. In this approach, we define a recursive function that sums the digits of the number and calls itself again with the new sum, continuing this process until the result is a single digit. While this is an elegant solution, it shares the same time complexity as the brute force method, d log 10 number, but introduces additional space overhead due to the recursive call stack. This added space complexity, can also lead to stack overflow for very large numbers. So, while recursion is an interesting alternative, its limitations make it less practical for larger inputs. Given the available options, the optimized mathematical approach, or digital root method, stands out as the best choice. Its O(1) time complexity and O(1) space complexity make it far more efficient than the brute force or recursive methods, particularly for large inputs. By avoiding iterative or recursive computations, it ensures both speed and scalability. While the brute force and recursive approaches are easier to understand and implement, they introduce performance overhead due to digit extraction and repeated operations. The mathematical method not only avoids these inefficiencies but also guarantees correctness through a simple yet powerful formula. This combination of efficiency, simplicity, and scalability makes the digital root approach the most practical and effective strategy for solving the add digits problem. To solve this problem, we are tasked with repeatedly summing the digits of a non-negative integer until only a single digit remains. For example, given the number 38, we first add its digits, 3 and 8, to get 11. Then, we repeat the process with 1 and 1 to get 2, which is the final result. This process is known as finding the digital root of a number. To approach this, we can start with a straightforward brute force method. First, if the number is already less than 10, it's already a single digit, so we can directly return it as the result. Otherwise, we repeatedly sum the digits of the number until it reduces to a single digit. Let's dive into how this iterative process works in detail. When the number is greater than or equal to 10, we extract its digits using the modulus operator % to get the last digit in integer division // to remove it. We then sum all these extracted digits and replace the original number with this sum. This process continues until the number becomes a single digit, at which point we return it as the result. While this brute force approach works, it can become inefficient for very large numbers because it involves repeatedly iterating through the digits. To optimize, we can use a mathematical property related to modular arithmetic. Specifically, the digital root can be computed in constant time using the formula 1 plus the remainder of number 1 divided by 9. This eliminates the need for the iterative summation process. For special cases, like when the input is 0, the result is also 0, and if the input is already a single digit, we return it immediately. This problem highlights the repetitive nature of reducing a number until a single digit is achieved. However, by recognizing the underlying mathematical property, we can bypass the iterative process entirely. The digital root formula leverages modular arithmetic to provide a constant time solution. This is a significant improvement over the brute force approach, which has a time complexity of O, k*d, where k is the number of iterations and d is the number of digits in the number. In contrast, the optimized approach has a time complexity of O(1). Both methods are space efficient, with a space complexity of O(1), as no additional data structures are required. This insight not only improves performance but also simplifies implementation. Now, let's look at the code implementations. In the brute force approach, we use a loop to repeatedly sum the digits of the number. Inside the loop, we calculate the sum of the digits by extracting each digit using the modulus operator and removing it using integer division. Once the sum is calculated, it replaces the current number, and the process repeats until the number becomes a single digit. On the other hand, the optimized approach directly applies the digital root formula. If the number is 0, we return 0. Otherwise, we use the formula 1 plus the remainder of number 1 divided by 9 to compute the single-digit result in constant time. These two approaches provide different trade-offs in terms of performance and simplicity, as we'll now analyze. For the brute force approach, the time complexity is O, k*d, where k represents the number of iterations required to reduce the number to a single digit, and d represents the average number of digits during each summation. The space complexity is O(1), as no additional memory is used beyond temporary variables. In contrast, the optimized approach has a time complexity of O(1), because the formula computes the result in constant time, regardless of the size of the input number. Its space complexity is also O(1), as no additional memory is required. This makes the optimized solution far more efficient for large numbers while still being simple and elegant in its implementation. This implementation solves that add digits problem using a straightforward iterative approach. The goal is to repeatedly sum the digits of a number until the result is a single digit. Explanation, step by step. 1. Outer while loop. The while number equals 10 loop ensures that we continue processing as long as the number has more than one digit. Once the number is a single digit, the loop stops. 2. Inner while loop. Inside the outer loop, we use an inner while number 0 loop to sum all the digits of the current number. This is done by repeatedly extracting the last digit using number %10 and adding it to the sum_digits variable. We then remove the last digit by performing integer division number // equals 10. 3. Update number. After summing all the digits, the number variable is updated to the value of sum_digits, and the process repeats if necessary. 4. Return the result. When the outer loop exits, the number is guaranteed to be a single digit, which is returned as the result. Key points. The solution avoids recursion to prevent stack overflow for very large numbers. It efficiently reduces the number digit by digit in each iteration. This approach handles all edge cases, including number equals 0, returns 0 immediately, and single digit inputs, returns the number itself. The time complexity is O log number, because the number of digits reduces with each iteration, and the space complexity is O1, since no additional memory is used apart from variables. This is the Java implementation of LeetCode problem number 258, add digits. The approach mirrors the Python logic, using a while loop to repeatedly sum the digits of the number until it becomes a single-digit value. Key differences include explicit type declarations for variables and the absence of Python-specific syntax. The logic remains identical: repeatedly sum the digits using modulo and division operations. We begin with an example where the input number is 38. Since 38 is greater than or equal to 10, we enter the outer while loop. In the first iteration, we initialize a variable sum_digits to 0. Now, we process the digits of the number within the inner while loop. First, we add the last digit of 38, which is 8, to sum_digits, resulting in a value of 8. Then, we remove the last digit from 38 by performing integer division by 10, leaving us with 3. Next, we continue in the loop and add the last digit of the updated number, which is now 3, to sum_digits. This results in a new sum_digits value of 11. After removing the last digit from 3, the number becomes 0, so we exit the inner loop. At this point, number is updated to the value of sum_digits, which is now 11. Now, with the updated number 11, we check again and see that it is still greater than or equal to 10, so we repeat the process. We reinitialize sum_digits to 0 and begin processing the digits of 11 in the inner while loop. First, we add the last digit, which is 1, to sum_digits, making it 1. Then, we remove this last digit from 11, leaving us with 1. Continuing, we add the last digit of the updated number, which is also 1, to sum_digits, resulting in a new value of 2. Removing the last digit from 1 leaves us with 0, so we exit the inner loop. We then update number to the value of sum_digits, which is now 2. At this point, since number is less than 10, we exit the outer loop and return the final result, which is 2. In another example, the input number is 123. Since 123 is greater than or equal to 10, we enter the outer while loop. In the first iteration, we initialize sum_digits to 0 and start processing the digits of 123 in the inner while loop. First, we add the last digit, 3, to sum_digits, resulting in a value of 3. We then remove this last digit from 123, leaving 12. Next, we add the last digit of 12, which is 2, to sum_digits, making it 5. Removing the last digit from 12 gives us 1. Finally, we add the last digit of 1 to sum_digits, resulting in 6. Removing this last digit leaves us with 0, so we exit the inner loop. We then update number to the value of sum_digits, which is now 6. Since 6 is less than 10, we exit the outer loop and return the result, which is 6. In the final example, the input number is 5. Since 5 is already less than 10, we skip the outer loop entirely and directly return the result, which is 5. From these examples, we can observe that the algorithm works by repeatedly calculating the sum of the digits of the input number until the result is a single digit. This is achieved by extracting digits with the modulus operator, number %10, and removing them using integer division, number // equals 10. Once the sum of digits is computed, it replaces the original number, and the process continues until the number is less than 10. The time complexity of this algorithm is approximately O log 10 number, because each iteration reduces the number of digits in the input. Additionally, the space complexity is O(1), as the algorithm operates with a constant amount of extra memory. To understand the time complexity of this implementation, we start by analyzing the number reduction process and the way digits are summed. First, consider the inner loop, where we extract each digit of the number using the modulo operation, number %10, and accumulate these digits into a sum. For a number with d digits, the loop iterates d times. Since the number of digits d is proportional to the base 10 logarithm of the number, or log 10 number, the inner loop has a time complexity of O log 10 number. Now, looking at the outer loop, it continues until the number reduces to a single digit. Each iteration of this loop performs a summation of the digits, which significantly reduces the size of the number. The number of iterations required is proportional to the logarithmic scale reduction of the number, which is also O log 10 number. This gives us the foundational analysis of the time complexity for both the inner and outer loops separately. When we combine the complexities of the inner and outer loops, we see that for each iteration of the outer loop, the inner loop performs O log 10 number work. Since the outer loop itself runs O log 10 number times, the total time complexity becomes the product of these two, which is O log 10 number caret 2. Now, for the space complexity, the algorithm uses a constant amount of extra space. This includes variables such as sum_digits and number, and no additional data structures are created that depend on the size of the input. As a result, the space complexity is O(1), making this implementation very efficient in terms of memory usage. When comparing this method to other approaches, a brute force strategy might involve converting the number to a string and iterating over its characters to sum the digits. While this has a similar time complexity, it uses additional space for the string conversion, making it less optimal in terms of space complexity. On the other hand, an optimized mathematical approach leverages the properties of digital roots to compute the result directly in O(1) time. This avoids iterative digit summation entirely and is the most efficient in both time and space. Finally, whether we consider best, average, or worst-case scenarios for the current implementation, the time complexity remains O log 10 number caret 2, because it depends solely on the size of number and the digit reduction process. The logarithmic reduction ensures that the time complexity is tightly bounded, and the space complexity remains O(1), since no additional memory is allocated during the computation. When working on the add digits problem, it's easy to make a few common mistakes that can affect your solution. One frequent issue is misunderstanding the problem statement. Remember, the goal is to reduce the number to a single digit by summing its digits repeatedly, not just stopping after one iteration. Missing this requirement can lead to incorrect results. Another potential pitfall is ignoring edge cases. For instance, handling inputs like 0, negative numbers, or extremely large values requires extra attention. These cases often reveal bugs or runtime errors if not explicitly accounted for. Efficiency is another important aspect. A brute force approach that repeatedly extracts and sums digits might work but can become inefficient for very large numbers, especially in competitive or interview settings. Finally, incorrect use of modulo arithmetic can cause errors. If you plan to use the digital root formula, such as en1, %9 plus 1, make sure you thoroughly understand its derivation and application to avoid miscalculations. Special cases in the formula approach also deserve careful consideration. For example, inputs like n equals 0 or numbers divisible by 9 need to be handled explicitly to ensure the formula doesn't produce unexpected results. Beyond these specific issues, interviews often emphasize broader problem-solving skills. Recognizing patterns, such as the use of modulo arithmetic or mathematical shortcuts in digit-based problems, can greatly simplify your solution and make it more elegant. Interviewers also appreciate when candidates demonstrate awareness of optimal approaches, like achieving O(1) complexity, while still acknowledging the trade-offs of simpler, more intuitive methods. Additionally, proactive testing of edge cases and discussing how your solution scales with large inputs can set you apart. Lastly, it's important to clearly explain your thought process during interviews. If you're using a mathematical formula, walk through its derivation step by step to showcase your understanding, rather than just quoting it from memory. This demonstrates depth in your approach. The add digits problem is closely related to several other digit-based problems on LeetCode, such as LeetCode 202, Happy Number, LeetCode 66, +1, and LeetCode 415, Add Strings. Exploring these related problems can help you build a stronger foundation in similar concepts. Now, let's look at some of the approaches you can use for solving this problem, along with their trade-offs. The brute force approach involves repeatedly extracting digits, summing them, and continuing this process until you reach a single digit. While this method is straightforward and easy to implement, its complexity is O log n per iteration, as the number of digits reduces logarithmically. This means it can become inefficient for very large numbers. On the positive side, it's simple and intuitive, which makes it a good starting point. However, it's essential to understand the trade-offs, particularly in terms of performance, when deciding whether to use this approach. An alternative and much more efficient approach is to use the mathematical formula for the digital root, expressed as n equals n1% 9 plus 1. This method directly computes the result in constant time, making its complexity O1. However, the trade-off is that it requires a clear understanding of how the formula works, as any misunderstanding can lead to incorrect results. Debugging errors in this approach can also be challenging if you don't fully grasp the underlying mathematics. Another option is the recursive approach, where you implement a function that sums the digits of the number and calls itself recursively until a single digit is obtained. While this approach often results in cleaner, more readable code, it shares a similar complexity to the brute force method and introduces the additional overhead of recursion. In some programming languages, this can even lead to stack overflow for extremely large inputs. Understanding these trade-offs is key to selecting the best approach for your needs. Great job on completing this problem. In summary, we explored both a brute force and an optimized approach to solve the add digits problem. Key takeaways include the power of understanding mathematical properties to simplify algorithms. Thanks for watching, and don't forget to like and subscribe for more coding insights. See you in the next walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!